So in today's video, we're going to be solving a system of two first orders ODEs. So in the last video that you guys saw, we were basically breaking up a second order ODE into two first orders ODE. But now what we're doing is we just have two random first order ODEs. Let's say you have a system of like multiple sets. You have a mass, um, a spring, a damper, or whatever. You just have multiple first order ODEs that you need to solve. But instead of solving each one individually, you can put them together in a matrix and solve all of them simultaneously. So let's see how we will do that. So the example that we have here, let's say we were given this. We have y1 prime as a function, the function of t is equal to -3 y1 plus y2, and y2 prime, also a function of t, it's equals to y1 minus y2. All right, so this is basically what we're getting. This is basically the system that we need to solve. So basically, we don't need to do the first steps that we did in the other video of breaking second order ODE. In this one, we're pretty much given the system already. All we need to do is put it into matrix form. And you can see we have a matrix for the y1 primes, a matrix for the coefficients, the coefficient matrix A, and then a matrix for that for the variables y1 and y2. So we skip all the other steps of defining y1 and defining y2. That usually only applies when you're breaking a higher order into a lower order. But in this case, we're already given our two first order ODEs, so we can skip all of that and we can just put them into matrix form right away. So after this, our process is to find the eigenvalues. And if you remember how to find eigenvalues, you will know that we will get them by solving or finding the determinant of matrix A minus lambda times I equals to 0. So let's do that. So we have here our matrix A, the determinant, and you can see once again only the diagonals because of the identity matrix. That's how it looks like. Only the numbers in the diagonal will be subtracted by lambda. So since this is a determinant, we will basically multiply across -3 lambda times -3 lambda minus 1 times 1 equals to 0. And this is basically how it looks like. So after we multiply and we simplify everything, we're gonna get lambda squared plus 6 lambda plus 9 minus 1 equals to 0. Let's simplify and we get lambda squared plus 6 lambda plus 8 equals to 0. In this case, this one can be factored out. Of course, you can also always use quadratic equation for the roots or the eigenvalues as they're known in this problem. So we have lambda plus 2 times lambda plus 4 equals to 0. And if we solve for the lambdas, we're going to get that they're equal to -2 and -4. Okay, so now what will be the next step? And it will be using each lambdas to find the eigen vectors. So let's use lambda 1 first. So if you remember, the eigenvectors, they're found by solving matrix A minus lambda times I times X and setting that equal to 0. So starting with lambda 1 equals to -2, we'll get here our first augmented matrix. We have -3 minus -2, 1, 1, and -3 minus -2, 0, 0, times x1, x2. So let's simplify this. It just simplifies to -1, 1, 1, and -1. So you can see basically both rows are the same. Just the second row, it's the negative of the first row. So let's get rid of the second row. And we'll do that by just simply adding the first row to the second row. And that will give us our new row 2, which is just a line of zeros. So let's now multiply the matrices. And we're going to end up with -x1 plus x2 equals to 0. Let's assume that if x1 was 1, right? That's what we always do. Assume that x1 is 1. We always want to start with the simplest value. So if we assume that x1 is equals to 1, And then after we rearrange things, we're gonna end up then that x2 will also equals 1. And therefore, my first eigenvector, this is basically the way that you write your vectors. You can see it's an x and just like a little parenthesis 1. It's equal to 1, 1. That's my first eigenvector. You can see it's pretty straightforward, pretty easy. This is one of like the easiest chapters and problems to do, at least when they're like this, like 2 first order ODEs. So let's do the next one. So now we're gonna do for lambda 2 equals to -4. We repeat the process. We have matrix A, -3 minus -4, 1, 1, -3 minus -4. We simplify, and we're gonna end up with 1, 1, 1, 1, 0, 0 times x1, x2. In this case, you can see both rows are identical. So to get rid of the second row, we can just subtract both rows, and that will make us the second row to be just zeros. So after we multiply the two matrices, we're gonna end up with x1 plus x2 equals to 0. And if we assume x1 to be 1, then for this to be true, for this to be equal to 0, it means that x2 must equals -1. And therefore, my second eigenvector, it's nothing but 1 and -1. You can see pretty straightforward. Now we're gonna solve this, and we're gonna write the general solution, which is the form of y1 and y2 is equals to c1 times my first eigenvectors times e to the negative lambda 1 times t in this case, because we specified at the beginning that this problem was a function of t, plus c2 times my second eigenvectors times e to the lambda 2, which is my second eigenvalue, times t. So we substitute everything that we found out, and we're gonna get here then that this will be y1, y2 is equals to c1 times 1 and 1, e to the -2t, plus c2, 1 and -1, times e to -4t. And once again, this was our t's because we specified at the beginning that these two functions, or these two equations of y's, they were functions of t's. If they were functions of x, then we would write x instead of t, or whatever other variable we were specifying at the beginning. So this is my general solution. Of course, we can break these two into the y1 and y2 equations and find out whatever they are. But in this case, one is not the derivative of the other. That only applies when we're breaking a second order and because of everything that we defined at the beginning with the variables. But in this case, since these ones are just like two independent first order ODEs, they're basically in a way not related. Our two solutions are also not necessarily related to each other. They don't have to be the derivative of the other or something like that. So this is what my general solution will be. This will be the end of my problem, and that will be it. So I hope that this video was useful. Once again, if you need more examples, we'll do more videos like this. So you can go and see the other one that we did before of breaking a second order. But up to this moment, that's it. So hope that this was helpful, and as always, good luck.